The death of a star is one of the most violent spectacles in the universe, a moment when gravity and light collide in an explosion so powerful it can outshine entire galaxies. A supernova. We imagine these stellar deaths as distant fireworks. Dramatic, yes, but comfortably far away. Yet what if one happened close to us? Not millions of light years out in another galaxy, but frighteningly near, within our own stellar neighborhood. From the frozen deserts of Earth's poles to the bustling lights of our cities, the world would change in an instant. The night sky would not darken, it would blaze. A new star, brighter than the full moon, would burn in the heavens, and with it would come invisible dangers, torrents of radiation, waves of cosmic energy, and storms of charged particles tearing into our planet's fragile shield. But before we dive into this terrifying scenario, I want to know something. Where in the world are you watching from, and what time is it for you right now? It is always extraordinary to imagine people scattered across the globe, each of us standing beneath the same sky, bound together by questions that transcend time and place. If you are fascinated by these journeys into the mysteries of the universe, subscribing will ensure you never miss the next exploration. Each story takes us deeper into the unknown, where science and imagination meet. Now, let us return to the dying star. Because when a supernova erupts close to our solar system, it is not just a cosmic event. It is a story of survival, extinction, and the fragile balance that keeps life on Earth alive. This could change everything we know. Recent scientific discoveries have made this scenario more relevant than ever. In 2025, researchers found evidence that a supernova explosion struck Earth approximately 10 million years ago, leaving traces in Pacific Ocean sediments. The discovery of elevated beryllium-10 isotopes, cosmic fingerprints left by high-energy particles, suggests that our planet has already experienced the effects of nearby stellar death. This isn't science fiction. It's scientific fact written in the rocks beneath the ocean floor. The evidence comes from deep-sea ferromanganese crusts that recorded a dramatic spike in cosmogenic isotopes between 11.5 and 9.0 million years ago. These isotopes form when cosmic rays slam into Earth's atmosphere, creating radioactive signatures that persist for millions of years. The discovery team, led by researchers from the University of Vienna, calculated a 68% probability that at least one star exploded within 326 light-years during this period. But this ancient supernova was relatively distant, close enough to leave traces, but far enough to avoid catastrophic damage. What would happen if the next one occurs much closer? Every star is a balancing act between two fundamental forces. Gravity pulls inward, trying to crush the stellar material into an infinitely dense point. Nuclear fusion pushes outward, releasing light and heat that creates the radiation pressure necessary to maintain stellar structure. For billions of years, this delicate equilibrium allows stars like our Sun to shine steadily, converting hydrogen into helium in their cores through the same process that powers hydrogen bombs. But when massive stars, those at least 8 times the mass of our Sun, reach the end of their lives, this balance collapses catastrophically. Their nuclear fuel becomes exhausted. Fusion falters and eventually stops entirely. Without the outward pressure of nuclear reactions, gravity wins decisively. The star's core implodes in a fraction of a second, compressing matter to densities comparable to atomic nuclei. Then, in a violent rebound, the outer layers blast outward at speeds approaching 30,000 kilometers per second, roughly 10% the speed of light. This is a core collapse supernova, designated Type 2 by astronomers. The core contracts into either a neutron star, a city-sized object containing more mass than our Sun, or, if the progenitor star was massive enough, a black hole. Meanwhile, the explosive shockwave tears through the star's outer layers, heating them to temperatures exceeding 100 billion degrees Celsius and accelerating them to phenomenal velocities. The second type of supernova, type Aya, follows a different but equally dramatic path. These explosions occur in binary star systems where a white dwarf, the dense Earth-sized remnant of a star like our Sun, slowly accumulates material from a companion star. The white dwarf acts like a cosmic vampire, feeding on its stellar partner for millions of years. When the white dwarf's mass approaches the Chandrasekhar limit of about 1.4 solar masses, it can no longer support itself against gravitational collapse. The entire star detonates in a runaway thermonuclear explosion, completely destroying itself in the process. Both types are unimaginably powerful. In mere seconds, a supernova releases more energy than the Sun will produce in its entire 10 billion-year lifespan. To put this in perspective, our Sun outputs approximately 3.8 spawn 10^26 watts continuously. A supernova releases about 10^44 joules of energy, equivalent to the Sun's total lifetime energy output, in just 10 seconds. This energy release is so enormous that for a brief period, a single exploding star can outshine an entire galaxy containing 100 billion stars. The explosion creates and disperses heavy elements throughout the cosmos. In the extreme temperatures and pressures of a supernova, nuclear fusion processes that are impossible under normal stellar conditions can occur. Elements heavier than iron, including gold, platinum, uranium, and many others essential to rocky planets and life, are forged in these cosmic furnaces. Without supernovae, the universe would contain only hydrogen, helium, and trace amounts of lithium. There would be no carbon, no oxygen, no silicon for rocks, no iron for blood. We are, quite literally, made of stardust, the ashes of ancient stellar explosions that occurred billions of years ago. The calcium in our bones, the iron in our blood, the gold in our jewelry, all were created in the nuclear cauldrons of dying stars and scattered across space by supernova explosions. In this sense, supernovae are both destroyers and creators, agents of death and birth operating on cosmic scales. From a safe distance of thousands of light years, supernovae are spectacular and beneficial events. They enrich the interstellar medium with heavy elements, trigger the formation of new stars by compressing nearby gas clouds, and create the chemical diversity necessary for planet formation and life. Astronomers observe dozens of supernovae each year in distant galaxies, studying them to understand stellar evolution, cosmic distances, and the expansion of the universe. But proximity changes everything. Distance provides safety in space, as energy spreads out according to the inverse square law. Double the distance, and the energy per unit area drops by a factor of 4. Most supernovae are comfortably distant, their energy dissipated across the vast emptiness between stars. However, when a supernova occurs within our cosmic neighborhood, it becomes not a spectacle to admire, but a potential existential threat. Astronomers estimate that a supernova within 30 light-years of Earth would be catastrophic for life on our planet. At that distance, the initial burst of high-energy radiation, X-rays and gamma rays, would arrive within hours of the explosion, traveling at the speed of light. This radiation would interact with our atmosphere in ways that could fundamentally alter Earth's chemistry and climate. The high-energy photons would penetrate the stratosphere and break apart nitrogen and oxygen molecules, creating nitrogen oxides that destroy ozone. Our POW, protective ozone layer, which shields the surface from harmful ultraviolet radiation, would be severely depleted. Within weeks, UV levels at Earth's surface could increase dramatically, making sunlight lethal to many forms of life. Beyond 100 light-years, the effects would weaken but remain significant. Even at distances of several hundred light-years, a powerful supernova could cause noticeable climate disturbances, increased background radiation, and subtle but profound stresses on ecosystems. The cosmic ray flux, high-energy particles accelerated by the supernova shockwave, would remain elevated for thousands of years, creating a persistent source of additional radiation. Recent research published in Nature Communications in 2024 suggests that Earth's atmosphere provides more protection than previously thought. Using advanced Earth system models that incorporate comprehensive atmospheric chemistry and cloud formation processes, scientists found that the effects of nearby supernovae might be less severe than earlier estimates predicted. However, even these optimistic models show significant regional effects, particularly at high latitudes where Earth's magnetic field provides less protection from cosmic radiation. The sobering reality is that supernovae are not distant curiosities safely confined to other galaxies. Our Milky Way galaxy experiences approximately 2 to 3 supernova explosions per century. Most occur in the dense star-forming regions of the galactic spiral arms, but some happen closer to home. The galaxy is a dynamic, violent place where stellar death is a regular occurrence. So where is the nearest threat? Which stars in our cosmic neighborhood might explode? And when? When astronomers and the public think of potential supernova candidates, one name dominates the conversation: Betelgeuse. This massive red supergiant star, clearly visible as the ruddy shoulder of Orion the Hunter, represents one of the most famous and closely watched stellar time bombs in our galaxy. Betelgeuse is a monster among stars. With a mass estimated between 15 and 20 times that of our Sun, it has evolved into a red supergiant of truly staggering proportions. If this bloated stellar giant were placed at the center of our solar system, its surface would extend well beyond the orbit of Mars, and possibly as far as Jupiter. The star is so large that its diameter varies by amounts comparable to the Earth-Sun distance as it pulsates and changes brightness. This variability has made Betelgeuse a subject of intense scrutiny, particularly since late 2019 when the star began an unprecedented dimming event. Starting in October 2019, Betelgeuse faded dramatically, dropping from its usual magnitude of about 0.5 to a minimum of 1.7 by February 2020. For a star that had been monitored for centuries, this behavior was extraordinary and alarming. The dimming was so pronounced that it was easily visible to the naked eye, leading to widespread speculation that Betelgeuse might be on the verge of exploding. The Great Dimming, as astronomers dubbed it, triggered intense observational campaigns using space-based and ground-based telescopes around the world. Initial theories ranged from dust clouds ejected by the star to fundamental changes in the stellar interior that might signal an impending core collapse. The possibility that humanity might witness a supernova in real time and at such close range captured both scientific and public imagination. However, subsequent analysis revealed that the dimming was most likely caused by a massive dust cloud ejected from the star's source, our face. Betelgeuse, like many red supergiants, is prone to violent mass ejections as it struggles to maintain stability in its final evolutionary phases. The dust cloud temporarily blocked some of the star's light from reaching Earth, creating the dramatic dimming effect. By mid-2020, Betelgeuse had returned to normal brightness, and by 2023, it actually reached its brightest level in recorded history. Recent observations have added new complexity to our understanding of Betelgeuse. In 2025, astronomers using advanced interferometry techniques made a remarkable discovery. Betelgeuse appears to have a faint stellar companion. This hidden companion star, if confirmed, could significantly affect Betelgeuse's evolution and eventual explosion. Binary interactions can trigger earlier supernovae, alter the explosion mechanism, or even prevent core collapse under certain circumstances. The discovery of a potential companion also helps explain some of Betelgeuse's unusual behavior over the centuries. Historical records from Chinese, Arab, and European astronomers show that Betelgeuse has varied in brightness throughout recorded history, sometimes being described as brighter than Rigel, the blue supergiant that forms Orion's foot, and other times appearing significantly dimmer. These variations might result from complex interactions between Betelgeuse and its companion, affecting the primary star's mass loss rate and surface conditions. Despite the drama surrounding Betelgeuse's variability, current estimates suggest that the star is not immediately approaching core collapse. Red supergiants like Betelgeuse can maintain their inflated state for hundreds of thousands of years before finally exhausting their nuclear fuel. While the star will certainly explode as a supernova at some point in the cosmically near future in astronomical terms could mean anywhere from tomorrow to 100,000 years from now. When Betelgeuse finally does explode, it will create one of the most spectacular sights in human history. The supernova will be visible during daylight hours, appearing as bright as a half moon in the night sky. For several weeks, Earth will effectively have two suns, our normal sun during the day and the blazing supernova remnant of Betelgeuse at night. Shadows will be cast by moonlight and the night sky will be bright enough to read by. But here lies the crucial point. Betelgeuse is safe. Located approximately 642 light-years from Earth, the star is far enough away that its explosion will be a magnificent spectacle rather than a catastrophe. The high-energy radiation will be diluted by distance to levels that pose no significant threat to life on Earth. We will witness one of nature's most powerful phenomena without suffering its destructive effects. This safety margin, however, should not lull us into complacency. Betelgeuse represents just one type of supernova candidate, and it happens to be located at a comfortable distance. Other types of stellar explosions pose greater risks, particularly those involving much more massive stars or stars with different evolutionary pathways. Wolf-Rayet stars represent a far more dangerous class of supernova progenitors. These are extremely massive stars, typically 25 to 50 solar masses, that have stripped away their outer hydrogen layers through violent stellar winds, exposing their helium-rich cores. Wolf-Rayet stars burn through their fuel at prodigious rates, living only a few million years before exploding as core collapse supernovae. More ominously, many Wolf-Rayet stars are thought capable of producing gamma-ray bursts, focused beams of the most energetic electromagnetic radiation in the universe. Several Wolf-Rayet stars exist within the critical 100 light-year radius around Earth. WR-104, located about 20,600 light-years away in the constellation Sagittarius, has been nicknamed the Pinwheel of Death due to its distinctive spiral structure and potential to produce a gamma-ray burst. While recent observations suggest that WR-104's rotational axis is not pointed directly at Earth, reducing the threat from a potential gamma-ray burst, other Wolf-Rayet stars in our vicinity remain poorly studied. The key difference between Wolf-Rayet explosions and those of red supergiants like Betelgeuse lies in the energy release mechanism. While both produce powerful supernovae, Wolf-Rayet stars can also generate collimated jets of gamma rays if their cores collapse into rapidly rotating black holes. These gamma-ray bursts represent the most energetic explosions in the universe, capable of delivering lethal doses of radiation across distances of thousands of light-years. Recent surveys using the European Space Agency's Gaia spacecraft have revolutionized our understanding of stellar motions and distances in our local galactic neighborhood. By precisely measuring the positions and velocities of over 1 billion stars, Gaia has allowed astronomers to trace stellar orbits backward in time, identifying which stars or star clusters might have been close to Earth in the past. This technique was used in the 2025 study that identified potential supernova sources for the beryllium-10 anomaly found in Pacific Ocean sediments. By rewinding the orbits of 2,725 open star clusters over the past 20 million years, researchers identified several cluster systems that could have hosted exploding stars at the right time and distance to explain the isotopic evidence. The analysis revealed that the Sun's path through the galaxy has brought us through several active star-forming regions over the past 10 million years. Around 10 million years ago, our solar system was passing through or near the Radcliffe Wave, a 9,000 light-year-long chain of gas clouds and young star clusters that forms the backbone of local star formation in our region of the galaxy. This raises a sobering question. If supernovae have affected Earth in the past, what about the future? Are we currently on a collision course with other dangerous stellar neighborhoods? The Earth carries scars of past cosmic violence written not in visible craters but in the atomic signatures preserved in rocks, sediments, and even living organisms. These traces tell a story of stellar death and its consequences for life on our planet, a story that has only recently begun to be deciphered. The discovery of iron-60 in ocean sediments represents one of the most compelling pieces of evidence for nearby supernova explosions in Earth's recent history. Iron-60 is a radioactive isotope with a half-life of 2.6 million years, long enough to travel through interstellar space, but short enough that any iron-60 found on Earth must have been created relatively recently in cosmic terms. This isotope cannot be produced naturally on Earth through any known geological or atmospheric processes. Its presence is the unmistakable fingerprint of stellar nucleosynthesis and supernova explosions. The story began in 2004 when German scientists reported finding iron-60 in deep-sea ferromanganese crusts collected from the Pacific Ocean. These crusts form extremely slowly over millions of years as metals precipitate from seawater onto the ocean floor. They act like geological tape recorders, preserving the chemical composition of the ocean at different times in Earth's history. The discovery of iron-60 in specific layers of these crusts indicated that sometime between 1.5 and 3.2 million years ago, our planet was showered with debris from one or more nearby supernova explosions. Subsequent investigations have expanded and refined this timeline. Studies of sediment cores from multiple ocean basins have revealed not one but two distinct periods of iron-60 deposition. The first occurred approximately 2.6 million years ago, and the second around 6.5 million years ago. These dual signals suggest that our solar system has passed through regions of space contaminated by supernovae, a debris on multiple occasions. The 2025 discovery of elevated beryllium-10 isotopes in Pacific ferromanganese crusts has added another layer to this story. Unlike iron-60, which arrives as dust particles from the explosion site, beryllium-10 is produced when cosmic rays interact with Earth's atmosphere. The isotope serves as a record of cosmic ray flux. Higher beryllium-10 concentrations indicate periods when Earth was bombarded by more high-energy particles from space. The beryllium-10 anomaly, dated to approximately 10.1 million years ago, represents evidence of a third supernova event affecting Earth. The timing suggests that our solar system encountered the cosmic ray shockwave from this explosion before the slower-moving dust and debris arrived. This sequence makes sense. Cosmic rays travel at nearly the speed of light, while supernova ejecta moves at only a few % of light speed. The beryllium-10 spike thus represents the leading edge of the stellar explosion's effects on Earth. These findings have profound implications for understanding the relationship between cosmic events and life on Earth. The periods of supernova activity coincide with several significant changes in Earth's climate and biosphere. The iron-60 deposition around 2.6 million years ago occurred during the Pliocene-Pleistocene boundary, a time of major climate transitions that saw the onset of extensive northern hemisphere glaciation and significant changes in global ocean circulation patterns. Some researchers have proposed direct connections between nearby supernovae and these environmental changes. The cosmic ray bombardment associated with supernova explosions could have depleted Earth's ozone layer, allowing increased ultraviolet radiation to reach the surface. This enhanced UV radiation would have stressed terrestrial ecosystems, potentially contributing to evolutionary pressures that drove speciation and extinction events. The mechanism involves complex atmospheric chemistry. High-energy cosmic rays entering Earth's atmosphere break apart nitrogen and oxygen molecules, creating nitrogen oxides, NOx, and hydrogen oxides, HOX. These compounds participate in catalytic cycles that destroy ozone molecules in the stratosphere. Even relatively modest increases in cosmic ray flux can lead to significant ozone depletion, particularly at high latitudes where Earth's magnetic field provides less protection. Computer simulations of these processes suggest that the cosmic ray increases associated with nearby supernovae could have reduced global ozone levels by 10 to 30% for periods of several thousand years. Such ozone depletion would have been most severe at polar latitudes, creating strong gradients in UV exposure between equatorial and polar regions. These gradients could have driven evolutionary adaptations, migration patterns, and ecosystem restructuring. The evidence extends beyond chemical isotopes to biological systems. Some researchers have found elevated mutation rates in pollen and spores preserved in sediments from the relevant time periods, suggesting increased genetic damage from cosmic radiation. Marine organisms show signs of stress during these intervals, with changes in shell chemistry and population dynamics that could reflect altered ocean conditions. Perhaps most intriguingly, the timing of these supernova events overlaps with important evolutionary developments in early human ancestors. The transition from Australopithecus to early Homo species occurred around 2.8 million years ago, very close to the first iron-60 deposition event. While it would be premature to claim a direct causal relationship, the coincidence raises fascinating questions about whether cosmic events might have influenced human evolution. The supernova hypothesis suggests that increased cosmic radiation could have accelerated mutation rates in early hominins, providing additional genetic variation for natural selection to act upon. The environmental stresses associated with ozone depletion, including increased UV radiation, climate instability, and ecosystem disruption, might have favored the evolution of traits like increased brain size, tool use, and behavioral flexibility that characterize the Homo lineage. However, establishing definitive causal relationships between cosmic events and evolutionary changes remains challenging. Earth's climate and biosphere are influenced by many factors, including plate tectonics, ocean circulation changes, solar variability, and internal ecosystem dynamics. Teasing apart the specific contributions of supernova effects requires careful analysis of multiple independent lines of evidence. Recent advances in analytical techniques are providing new tools for these investigations. Accelerator mass spectrometry can now detect individual atoms of rare isotopes like iron-60 and beryllium-10 in extremely small samples. This sensitivity allows researchers to create detailed time series of cosmic ray exposure with temporal resolution of thousands or even hundreds of years. Archaeological sites are beginning to yield traces of cosmic isotopes in materials like meteorites, fossils, and ancient soils. These discoveries are expanding the geographical and temporal scope of supernova signatures on Earth. Some researchers are even investigating whether cosmic isotopes might be preserved in ice cores from Antarctica and Greenland, which could provide annual resolution records of supernova effects. The emerging picture reveals that Earth exists in a dynamic cosmic environment where stellar explosions regularly influence our planet's atmospheric chemistry, climate, and possibly even biological evolution. We are not isolated from the violent processes occurring elsewhere in the galaxy. We are participants in a cosmic ecosystem where the death of distant stars shapes the conditions for life on Earth. This realization has important implications for astrobiology and the search for life elsewhere in the universe. If nearby supernovae can significantly affect planetary atmospheres and biological systems, then the galactic environment becomes a crucial factor in determining where and when life can thrive. Regions of the galaxy with high supernova rates might be hostile to complex life, while quiet zones could provide more stable conditions for biological evolution. Our solar system appears to have experienced both conditions. The multiple supernova events recorded in Earth's geological record suggest that we periodically pass through active star-forming regions where stellar explosions are common. Currently, we reside in what astronomers call the local bubble, a cavity in the interstellar medium created by supernova explosions over the past 14 million years. This bubble provides some protection from cosmic rays, but it also places us in a region that has recently experienced multiple stellar deaths. The question that emerges from this evidence is both sobering and urgent. If nearby supernovae have affected Earth multiple times in the past, what are the chances of another event in the near future? And if such an event occurs, how close would it need to be to pose a serious threat to human civilization and life on Earth? To understand the true danger of a nearby supernova, we must examine what would happen if a massive star exploded within the critical distance of 30 light-years from Earth. At this range, the effects would be immediate, severe, and potentially civilization-ending. The sequence of events would unfold with terrifying precision, turning our familiar sky into an agent of destruction. The first herald of doom would be invisible and nearly instantaneous. Moments after the stellar core collapses, a flood of neutrinos would race outward from the explosion site at nearly the speed of light. These ghostly particles, which barely interact with matter, would pass through Earth in vast numbers, trillions upon trillions streaming through every square centimeter of our planet. While neutrinos pose no direct threat to life, their detection by sensitive instruments would provide humanity with its only advance warning of the catastrophe to come. Neutrino detectors scattered across the globe, facilities like Super Kamiokande in Japan, Ice Cube in Antarctica, and Dune in the United States, would register the surge within hours of the stellar collapse. Scientists would immediately recognize the signature as evidence of a nearby supernova. But this warning would be brief, lasting only hours or days before the real destruction arrived. Following the neutrino wave would come the light, a brilliant flash announcing the birth of a new star in Earth's sky. Depending on the exact distance and type of explosion, this supernova would appear as bright as the full moon or even brighter. Unlike the gentle, steady light of our moon, this new celestial beacon would blaze with the intensity of a stellar furnace, visible even in broad daylight. For weeks or months, Earth would have two sources of illumination, our sun by day and the supernova by night. The psychological impact on human civilization would be immediate and profound. Throughout history, the appearance of bright new stars has been interpreted as omens of great change, disaster, or divine intervention. A supernova bright enough to read by at midnight would trigger widespread panic, religious fervor, and social upheaval even before its more dangerous effects became apparent. Social media would explode with speculation, conspiracy theories, and apocalyptic predictions. Financial markets would likely collapse as investors fled to perceived safe havens. But the true danger would arrive days to weeks after the initial light flash, carried by invisible messengers of destruction, high-energy photons and cosmic rays traveling at nearly the speed of light. This electromagnetic radiation, primarily X-rays and gamma rays, would slam into Earth's atmosphere with unprecedented intensity, beginning a cascade of chemical reactions that would fundamentally alter our planet's protective envelope. The atmosphere would become a battlefield between incoming radiation and the molecules that comprise our air. High-energy photons would tear apart nitrogen and oxygen molecules in the stratosphere, creating highly reactive atomic fragments. These fragments would quickly combine to form nitrogen oxides, NOx, and hydrogen oxides, 8-ox, compounds that serve as catalysts for ozone destruction. Ozone depletion would begin within days of the radiation's arrival and accelerate rapidly. Our protective ozone layer, which normally absorbs 97–99% of the sun's harmful ultraviolet radiation, would be systematically dismantled by the reactive compounds created by cosmic ray bombardment. Computer simulations suggest that a supernova at 30 light-years could destroy 90% or more of the ozone layer within weeks. The loss of ozone protection would transform sunlight from life's energy source into an instrument of death. Ultraviolet B radiation, normally blocked by the stratosphere, would pour down unimpeded onto Earth's surface. The UV index, a measure of solar ultraviolet intensity, would skyrocket from typical values of 311 to levels exceeding 15 to 20 or even higher at some latitudes. At these intensities, unprotected human skin would burn within minutes of sun exposure. Outdoor activities would become impossible without extensive protective equipment. Even brief exposures could cause severe burns, cataracts, and DNA damage leading to cancer. The effects would be most severe at high latitudes, where the cosmic rays penetrate most easily due to the shape of Earth's magnetic field, but no region would be completely safe. The visual appearance of the sky itself would change in ominous ways. Without ozone to absorb ultraviolet light, the atmosphere's optical properties would shift noticeably. The sky would take on an unusual deep blue or violet tint during the day, while twilight would be marked by unnatural colors as scattered light interacted with the altered atmospheric chemistry. These beautiful but sinister hues would serve as a constant reminder that the very air around us had been transformed into something alien and hostile. Night skies would become spectacular and terrifying. The enhanced cosmic ray bombardment would create auroras visible at all latitudes, not just near the poles. Shimmering curtains of green, red, and purple light would dance across the entire globe as high-energy particles interacted with atmospheric gases. While beautiful to observe, these auroras would be symptoms of our planet's magnetic defenses being overwhelmed by the cosmic onslaught. The biological effects would manifest quickly and spread inexorably through Earth's ecosystems. Plants, which evolved under the protection of the ozone layer, would be among the first casualties. Crops would wither and die as their cellular machinery was damaged by ultraviolet radiation. Forests would begin to brown and lose their leaves, not from seasonal change, but from radiation damage. Photosynthesis, the fundamental process that supports most life on Earth, would be severely impaired. Marine ecosystems would face a particularly devastating collapse. Phytoplankton, microscopic plants that form the base of oceanic food chains, are extremely sensitive to ultraviolet radiation. These organisms live near the ocean's surface, where they normally rely on sunlight for photosynthesis. With the ozone layer depleted, the same sunlight would become lethal. As phytoplankton populations crashed, the effects would cascade up through the entire marine food web. Fish populations would decline rapidly as their food sources disappeared. Coastal regions that depend on fishing for protein and economic survival would face immediate crises. Coral reefs, already stressed by climate change and ocean acidification, would suffer massive bleaching events as both the corals and their symbiotic algae succumbed to radiation damage. On land, herbivorous animals would face starvation as plant communities collapsed. The loss of vegetation would also eliminate habitat for countless species, accelerating biodiversity loss. Predators would follow their prey into decline, creating a cascade of ecological collapse that would reshape ecosystems across the globe. Human civilization would find itself under siege from multiple directions simultaneously. Agriculture, the foundation of human society, would face unprecedented challenges. Crop yields would plummet as major food plants proved unable to survive in the high radiation environment. Wheat, rice, corn, and other staples would require protection under artificial shields or indoor growing facilities, infrastructure that most of the world lacks. The immediate response would likely involve emergency rationing, government control of food distribution, and massive international efforts to construct protected growing facilities. However, the scale of the required infrastructure would far exceed current global capacity. Hundreds of millions of people would face malnutrition or starvation within months of the supernova's arrival. Water resources would also come under threat. While the radiation itself might not contaminate water supplies directly, the collapse of natural ecosystems would affect water cycles and quality. Increased UV radiation would break down organic compounds in surface water, potentially creating toxic byproducts. The loss of vegetation would increase erosion and reduce the natural filtration of groundwater. Medical systems would be overwhelmed by the surge in radiation-related illnesses. Skin cancers, cataracts, and immune system suppression would affect millions of people who lacked adequate protection from enhanced UV radiation. The psychological stress of living under a hostile sky would exacerbate mental health problems on a global scale. Governments would likely implement emergency measures resembling wartime mobilization. Construction of underground shelters, covered walkways, and enclosed growing facilities would become national priorities. Some regions with existing underground infrastructure, such as certain urban areas or mining regions, might become refuges for larger populations. The technological response would focus on several critical areas. Space agencies would rush to deploy monitoring satellites to track the cosmic ray environment and predict radiation levels. Nuclear power plants and other critical infrastructure would need additional shielding to protect against enhanced cosmic ray bombardment. Communication systems would face increased interference from the radiation environment. But perhaps the most chilling aspect of a nearby supernova would be its duration. Unlike a nuclear war or asteroid impact, which cause immediate but relatively brief disruption, the effects of a supernova would persist for centuries or millennia. The cosmic ray bombardment would continue long after the initial explosion faded from view, maintaining elevated radiation levels and keeping the ozone layer suppressed. Recovery would be measured not in years or decades, but in geological timescales. Even if human civilization survived the initial crisis, it would face a permanently altered world where surface life requires constant protection from cosmic radiation. The open skies and natural environments that have characterized human existence throughout our species' history would become relics of a safer past. This scenario represents the ultimate test of human resilience and technological capability. A civilization capable of surviving a nearby supernova would need to fundamentally redesign its relationship with the environment, transitioning from surface-dwelling organisms dependent on natural ecosystems to a species capable of creating and maintaining artificial biospheres indefinitely. The question becomes not just whether we could survive such an event, but whether the civilization that emerged from it would still be recognizably human in its relationship to the natural world. In many ways, survival would require us to become something new. A species as comfortable underground as on the surface, as dependent on technology as on biology, as prepared for cosmic threats as terrestrial ones. One of the most terrifying aspects of the supernova threat is how little warning humanity would have before catastrophe struck. Unlike other cosmic dangers such as asteroid impacts, which can potentially be detected decades in advance, stellar explosions occur with shocking suddenness from our perspective. The final moments of a massive star's life unfold according to the laws of physics, not human timescales, and those laws are merciless in their precision. Understanding this timeline requires delving into the final stages of stellar evolution. For millions of years, a massive star slowly burns through its nuclear fuel, progressing from hydrogen fusion to helium fusion, then to the fusion of progressively heavier elements: carbon, oxygen, neon, silicon. Each stage burns faster and at higher temperatures than the last, like a cosmic hourglass running ever more quickly as the sand of stellar fuel runs out. The final stage, silicon fusion, lasts only days or weeks. During this brief period, the star's core reaches temperatures exceeding 3 billion degrees Celsius, hot enough to create iron peak elements through explosive nuclear reactions. But iron represents an energy dead end. Unlike lighter elements, iron fusion consumes energy rather than releasing it. When the core becomes predominantly iron, the star's long battle against gravity suddenly becomes hopeless. The collapse happens faster than human comprehension can easily grasp. In less than a second, perhaps just a few tenths of a second, the iron core shrinks from a sphere roughly the size of Earth to a neutron star only 20 kilometers in diameter. This is not a gradual process that unfolds over hours or days. It is a catastrophic implosion that occurs at approximately 30,000 kilometers per second, or 10% the speed of light. The physics of this collapse are so extreme that they create conditions found nowhere else in the universe except perhaps during the first moments after the Big Bang. Matter is compressed to nuclear density. A teaspoon of neutron star material would weigh as much as Mount Everest. The gravitational energy released in this collapse is staggering, roughly 100 times greater than the energy our Sun will produce over its entire 10 billion-year lifetime, released in a fraction of a second. Most of this energy emerges as neutrinos, ghostly particles that barely interact with matter. These neutrinos stream outward at the speed of light, carrying away 99% of the supernova's energy output. For the brief period of the collapse, the dying star produces more neutrinos than all the other stars in the observable universe combined. A supernova 30 light-years away would flood Earth with roughly 100 billion neutrinos per square centimeter, a number so large it defies intuitive understanding. Neutrino detectors on Earth would register this flood within hours of the stellar collapse, providing humanity's only advance warning of the approaching catastrophe. Current facilities like Super Kamiokande in Japan can detect neutrino bursts from supernovae throughout our galaxy. For a nearby explosion, the signal would be unmistakable. A sudden spike in neutrino counts unlike anything ever recorded. But this warning would be frustratingly brief. Neutrinos travel at essentially the speed of light, arriving only hours ahead of the electromagnetic radiation that carries the real danger. By the time scientists confirmed the neutrino detection and alerted government authorities, the window of opportunity for any meaningful preparation would already be closing. The light from the explosion would follow close behind the neutrinos. Unlike the steady illumination we're accustomed to from stars, the optical output of a supernova rises dramatically over the course of days or weeks. The explosion would first become visible as a new star in the constellation containing the progenitor. Within days, this new star would brighten to rival the brightest objects in the night sky. For a supernova at 30 light-years, the peak brightness would be extraordinary. The explosion would appear roughly as bright as the full moon, turning night into twilight across the entire planet. This cosmic lighthouse would be visible even during daylight hours, appearing as a brilliant white or blue-white star clearly visible against the blue sky. City lights would no longer be able to wash out the night sky. The supernova's glare would dominate even urban environments. The psychological impact of this celestial spectacle would be immediate and destabilizing. Throughout human history, the appearance of bright new stars has been interpreted as portents of disaster, divine intervention, or cosmic transformation. Ancient Chinese astronomers meticulously recorded such events as guest stars, while European chroniclers described them as harbingers of plague, war, or the death of kings. In our modern connected world, the social and economic disruption would be amplified exponentially. Social media platforms would explode with images, videos, and speculation about the new star. Conspiracy theories would proliferate faster than scientific explanations. Religious movements would interpret the event through various apocalyptic frameworks. Financial markets, already skittish about geopolitical uncertainties, would likely experience massive volatility as investors struggled to assess the implications of a cosmic event with no historical precedent in the modern era. Government responses would vary dramatically depending on scientific literacy, institutional capacity, and political stability. Nations with sophisticated space agencies and scientific establishments might mount coordinated emergency responses, but even these would be hampered by the unprecedented nature of the threat. Emergency planners prepare for earthquakes, hurricanes, pandemics, and even nuclear attacks, but few have considered the specific challenges posed by cosmic radiation bombardment. The most challenging aspect would be communicating the nature and timeline of the threat to the general public. Unlike familiar disasters that cause immediate visible damage, the dangerous effects of a supernova would be invisible and delayed. The brilliant new star in the sky would appear beautiful rather than threatening. The deadly cosmic rays and high-energy photons would arrive days or weeks later, providing no sensory warning of their approach. This delay between the visible explosion and the arrival of harmful radiation would create a critical period for preparation, if authorities understood what was coming and could mobilize resources effectively. The most immediate priority would be protecting power grids and electronic infrastructure from enhanced cosmic ray bombardment. High-energy particles can disrupt satellite communications, damage sensitive electronics, and interfere with power transmission systems. Space-based infrastructure would be particularly vulnerable. Satellites in orbit around Earth receive little protection from cosmic radiation compared to surface installations shielded by the atmosphere. The enhanced cosmic ray environment following a nearby supernova could disable GPS networks, communication satellites, weather monitoring systems, and scientific instruments. The loss of these capabilities would severely hamper disaster response and scientific monitoring efforts. Military and intelligence agencies would face unique challenges in distinguishing between supernova effects and potential hostile actions by foreign powers. Enhanced aurora activity might interfere with radar systems and early warning networks. Disruptions to satellite communications could be misinterpreted as electronic warfare attacks. The psychological stress of living under an alien sky might contribute to social unrest that could be misconstrued as organized subversion. International cooperation would become critically important, yet would occur under unprecedented circumstances. No existing treaty or diplomatic framework addresses the governance of global responses to cosmic threats. The effects of a nearby supernova would be felt worldwide, but with significant regional variations depending on latitude, local environmental conditions, and existing infrastructure. Developing nations with limited technological resources would be disproportionately affected, potentially creating massive refugee crises as populations sought shelter in regions with better protective infrastructure. The scientific community would face enormous pressure to provide accurate predictions about radiation arrival times, intensity levels, and geographical variations in effects. However, modeling the interaction between supernova radiation and Earth's atmosphere remains challenging even with modern computer simulations. Uncertainties in the initial explosion parameters, interstellar medium conditions, and atmospheric chemistry would limit the precision of forecasts precisely when precision would be most desperately needed. Research institutions would rush to redeploy their resources toward monitoring and characterizing the incoming threat. Radio telescopes would track the expanding shockwave, while atmospheric scientists would prepare to document changes in ozone levels and atmospheric chemistry. Medical researchers would begin planning studies of radiation exposure effects, while agricultural scientists would investigate methods for protecting crops and livestock. But ultimately, the most sobering aspect of the supernova countdown would be its inexorability. Unlike human-caused disasters, which might be prevented or mitigated through diplomatic intervention or technological fixes, stellar explosions follow the immutable laws of physics. Once a massive star's core begins its final collapse, no force in the universe can prevent the explosion or alter its effects. This cosmic countdown would proceed regardless of human hopes, fears, or actions. The radiation would arrive precisely when physics dictated. carry exactly the energy content determined by the progenitor star's mass and composition and affect Earth's atmosphere according to well-understood chemical processes. In facing such an event, humanity would confront its ultimate powerlessness against the fundamental forces that govern the universe. The supernova would serve as a stark reminder that Earth exists in a dynamic, violent cosmos where stellar death is as natural and inevitable as stellar birth. Our planet's habitability depends not only on its intrinsic properties, its size, atmospheric composition, and distance from the Sun, but also on its location within the galaxy and the current phase of stellar evolution in our cosmic neighborhood. This realization carries profound implications for how we understand our place in the universe and our responsibilities as a potentially spacefaring civilization. If life on Earth can be threatened by events occurring dozens of light years away, then humanity's long-term survival may ultimately depend on our ability to establish self-sufficient settlements beyond our home planet. The supernova threat becomes an argument not just for better disaster preparedness, but for becoming a truly interplanetary species. In the weeks following a nearby supernova explosion, human civilization would face challenges unlike any in our species' history. The familiar world of open skies, flourishing agriculture, and stable ecosystems would vanish, replaced by an alien environment where survival depends on constant vigilance against an invisible cosmic threat. The transformation would be as much psychological as physical, fundamentally altering humanity's relationship with nature and our sense of security on Earth. The first institutions to feel the strain would be medical systems worldwide. Hospitals and clinics would be overwhelmed by patients suffering from acute radiation exposure, severe sunburns from enhanced ultraviolet radiation, and eye damage from looking at the brilliant supernova. Emergency rooms would struggle to treat conditions rarely seen outside of nuclear accident zones or high-altitude aviation incidents. Dermatology wards would become overflowing centers for treating radiation burns. Even brief exposures to the enhanced UV environment would cause severe erythema, reddening and blistering of the skin that could require weeks of treatment. More serious cases would develop radiation dermatitis, with deep tissue damage, ulceration, and secondary infections. The normal human response to sun exposure, tanning, would be overwhelmed by the intensity of radiation, leaving even naturally dark-skinned individuals vulnerable to severe burns within minutes of outdoor exposure. Ophthalmologists would face an epidemic of cataracts, corneal damage, and retinal burns. The enhanced UVB radiation would be particularly damaging to eye tissues, which evolved under the protection of Earth's ozone layer. Even individuals who avoid looking directly at the supernova would suffer gradual damage from reflected and scattered radiation. Temporary or permanent blindness would become commonplace among those caught outdoors without adequate eye protection. More insidiously, the enhanced cosmic ray environment would begin affecting cellular DNA throughout the human population. While the effects would not be immediately visible, the increased mutation rate would manifest over months and years as elevated cancer rates, particularly skin cancers, leukemias, and tumors in radiation-sensitive organs. Reproductive health would be especially affected, with increased rates of miscarriage, birth defects, and genetic abnormalities in newborns. The psychological impact would be equally severe. Humans are creatures adapted to open environments with deep evolutionary programming that associates outdoor spaces with safety and opportunity. The sudden need to avoid sunlight, to treat the natural environment as inherently dangerous, would trigger widespread anxiety, depression, and claustrophobia. Mental health services would be overwhelmed by patients suffering from agoraphobia, panic disorders, and adjustment reactions to the transformed world. Agricultural systems would face immediate and catastrophic collapse. Crops in the field would begin showing signs of stress within days of the ozone depletion reaching critical levels. Leaves would yellow and develop brown spots as cellular chlorophyll was destroyed by UV radiation. Photosynthesis would be severely impaired, causing plants to stop growing and begin dying back. The timing of the supernova relative to growing seasons would determine whether agricultural collapse was measured in days or weeks, but the outcome would be inevitable without protection. Farmers would frantically attempt to construct shade structures over their fields, but the scale of agriculture makes comprehensive protection impossible with existing resources. A typical corn farm covers hundreds or thousands of acres, far too large to shelter with available materials. Even greenhouse agriculture would be affected, as conventional glass provides insufficient protection against the enhanced UV spectrum. Specialized UV-blocking materials would be required, creating instant shortages as global demand skyrocketed. The collapse of agriculture would trigger the most severe global food crisis in human history. Grain reserves might last months in wealthy nations, but developing countries with limited storage capacity would face starvation within weeks. International food aid would be complicated by the global nature of the crisis. No region would have surplus production to share with affected areas. Governments would likely implement emergency rationing programs, but the social stability required for such systems to function would be severely strained. Urban populations, normally dependent on complex supply chains bringing food from distant agricultural regions, would be particularly vulnerable. Cities would become death traps as food riots and social breakdown made organized distribution impossible. Livestock agriculture would face parallel crises. Cattle, sheep, and other animals adapted to outdoor grazing would suffer severe radiation burns on exposed skin areas. Dairy production would plummet as stressed animals stopped producing milk. Poultry kept in outdoor facilities would die in large numbers, while even indoor livestock would be affected by the lack of feed crops and the stress of confinement. Marine food resources would offer little relief. The collapse of oceanic phytoplankton populations would trigger a cascade of ecological failure throughout marine food webs. Fish populations would crash as their food sources disappeared, while coastal fisheries would be abandoned as UV radiation made surface waters uninhabitable for many species. Aquaculture facilities with outdoor ponds would face the same radiation challenges as terrestrial agriculture. Water resources would become increasingly critical as natural ecosystems collapsed. Surface water bodies would lose their natural biological filtration systems as aquatic plants and microorganisms died off. Enhanced UV radiation would break down organic compounds in water, potentially creating toxic byproducts that would require expensive treatment to remove. Groundwater would become increasingly important, but pumping and distribution systems would be challenged by power grid instabilities caused by cosmic ray bombardment. Energy infrastructure would face multiple simultaneous stresses. Solar panels, ironically, would become less effective due to degradation from enhanced radiation, while the panels themselves would require protection from UV damage. Wind turbines would need additional shielding for their electronic control systems. Nuclear power plants would require enhanced monitoring and protection for their cooling systems and electronic components. The enhanced cosmic ray environment would create persistent problems for electronic infrastructure. High-energy particles would cause more frequent failures in computer chips, memory systems, and communication networks. Satellite systems would be particularly vulnerable, with potential failures in GPS networks, weather monitoring, and telecommunications. The loss of these systems would severely hamper disaster response and coordination efforts. Urban environments would require rapid adaptation to the new reality. Cities would need to construct extensive covered walkway systems connecting residential areas to essential services. Existing underground infrastructure, subway systems, shopping centers, parking structures would become valuable refuges. Urban planning would shift dramatically toward underground development and enclosed spaces. The construction industry would face unprecedented demand for specialized materials and structures. UV-blocking glass, radiation-resistant electronics, and atmospheric filtration systems would be in critical shortage. Construction crews would require specialized protective equipment to work outdoors, dramatically slowing building projects when speed would be essential. Transportation systems would need complete redesign. Automobile travel would require vehicles with enhanced UV protection for windows and radiation shielding for occupants. Commercial aviation would be severely limited as high-altitude flight would expose passengers and crew to dangerous radiation levels. Shipping and logistics would be challenged by the need to protect workers and cargo from radiation exposure. Education systems would face the challenge of protecting children, who are particularly sensitive to radiation, while maintaining social development and learning. Schools would need to be converted to enclosed, protected environments or moved underground. Outdoor recreational activities that have been central to childhood development would become impossible, with unknown consequences for physical and psychological health. International relations would be strained by the global nature of the crisis and the unequal distribution of protective resources. Nations with extensive underground infrastructure, advanced technology, and large food reserves would be better positioned to survive, while developing countries would face humanitarian catastrophes on an unprecedented scale. Mass migration would be inevitable as populations fled regions with inadequate protection, potentially triggering conflicts over scarce resources and habitable areas. The economic system would require fundamental restructuring. Traditional agriculture-based economies would collapse, while industries focused on radiation protection, underground construction, and closed-loop life support systems would expand rapidly. Global trade would be disrupted by transportation challenges and the universal need to redirect resources toward survival infrastructure. Religious and philosophical systems would grapple with the theological implications of cosmic catastrophe. Some might interpret the supernova as divine judgment or a test of human faith, while others would struggle to understand why a supposedly beneficent universe would allow such random destruction. Secular worldviews would confront the ultimate demonstration of human vulnerability to cosmic forces beyond our control. Scientific institutions would become more crucial than ever, tasked with monitoring radiation levels, developing protective technologies, and researching methods for ecosystem restoration. However, the traditional open, collaborative nature of scientific research would be challenged by the need for immediate practical solutions and the breakdown of international communication systems. Perhaps most fundamentally, the supernova would force humanity to confront its assumptions about progress, technology, and our relationship with the natural world. The modern lifestyle of open spaces, global travel, and abundant food production would be revealed as dependent on cosmic conditions that can change without warning. Survival would require developing technologies and social systems capable of maintaining civilization in a permanently hostile environment. The generation that lived through the supernova event would be permanently marked by the experience. Children born after the explosion would grow up in a world where the surface is dangerous, the sky is hostile, and human survival depends on artificial protection from the cosmic environment. This psychological adaptation might be necessary for species survival, but it would represent a fundamental change in what it means to be human. Recovery would be measured not in years or decades, but in millennia. Even if civilization survived the initial crisis and adapted to the new conditions, the enhanced cosmic ray environment would persist for thousands of years. Returning to surface-based civilization would require either technological solutions for atmospheric protection or the slow natural recovery of Earth's ozone layer, a process that could take geological time periods. In many ways, surviving a nearby supernova would require humanity to become a fundamentally different kind of species, one as comfortable with underground habitats as surface environments, as dependent on technology as on natural ecosystems, and as prepared for cosmic threats as terrestrial ones. The civilization that emerged from such an event might bear little resemblance to the one that existed before, having been forged by necessity into something capable of thriving in a hostile cosmos. Despite their capacity for unimaginable destruction, supernovae represent the universe's most powerful creative forces. Every atom of iron coursing through your bloodstream, every trace of gold in your wedding ring, every molecule of calcium strengthening your bones, all were forged in the nuclear furnaces of dying stars and scattered across the cosmos by stellar explosions. The same cosmic violence that threatens life also makes life possible, creating a profound paradox at the heart of existence. To understand this cosmic alchemy, we must peer into the extreme conditions that exist only in the hearts of dying stars. During the final moments of a massive star's life, as its core collapses and rebounds in a supernova explosion, temperatures exceed 100 billion degrees Celsius and pressures reach values beyond terrestrial comprehension. Under these conditions, atomic nuclei are smashed together with such force that they overcome the electromagnetic barriers that normally prevent nuclear reactions. The result is a cascade of nuclear processes that cannot occur anywhere else in the universe. Elements heavier than iron, which cannot be produced by normal stellar fusion, are created through rapid neutron capture. In the intense neutron flux of a supernova explosion, atomic nuclei are bombarded with so many neutrons that they gain mass faster than they can decay, building up the periodic table's heaviest elements in mere seconds. Gold, platinum, uranium, thorium, all the elements that define technological civilization, are manufactured exclusively in these stellar death throes. The gold in our electronics, the platinum in our catalytic converters, the uranium that powers nuclear reactors, all are the ashes of ancient supernova that exploded billions of years ago, enriching the interstellar medium with the raw materials for planets and life. This process of cosmic nucleosynthesis was first understood in the 1950s through the pioneering work of physicists Fred Hoyle, William Fowler, and Jeffrey and Margaret Burbidge. Their landmark paper, colloquially known as B2FH, demonstrated that the universe's chemical complexity stems directly from stellar evolution and death. Stars are not just distant suns. They are cosmic factories manufacturing the elements essential for rocky planets, organic chemistry, and biological systems. The irony is profound. The same stellar explosions that could sterilize Earth are responsible for Earth's very existence. Without supernovae, the universe would contain only the light elements created in the Big Bang: hydrogen, helium, and traces of lithium. There would be no carbon for organic molecules, no oxygen for water, no silicon for rocks, no iron for blood. The cosmos would be a barren collection of gas clouds and simple stars, incapable of supporting the chemical complexity that makes life possible. This duality extends beyond mere element creation to the large-scale structure of galaxies and the formation of new stellar systems. Supernova shockwaves compress nearby gas clouds, triggering gravitational collapse and star formation. The same explosions that destroy also create, fostering the birth of new generations of stars enriched with heavy elements from their predecessors' death. Our own solar system bears the chemical fingerprints of multiple supernova explosions that occurred before the Sun's formation 4.6 billion years ago. The abundance patterns of elements in meteorites, lunar samples, and Earth's crust tell a story of gradual chemical enrichment over cosmic time. Each supernova added its unique signature to the growing inventory of heavy elements available for planet formation. Recent isotopic studies have revealed that our solar system's formation may have been directly triggered by a IRB supernova explosion. Certain short-lived radioactive isotopes found in primitive meteorites could only have been created in a stellar explosion and incorporated into the solar nebula within a few million years of their creation. This suggests that a supernova shockwave not only provided the heavy elements for planetary formation, but also compressed the gas cloud that would become our solar system, initiating the gravitational collapse that led to the Sun's birth. The biological implications of this cosmic inheritance are staggering. Life as we know it depends entirely on the chemical complexity made possible by supernova nucleosynthesis. The carbon atoms that form the backbone of organic molecules, the phosphorus in DNA, the sulfur in proteins, the trace metals that catalyze biochemical reactions, all are gifts from dying stars. But the relationship between supernovae and life extends beyond passive element donation to active evolutionary pressure. The multiple supernova events recorded in Earth's geological history suggest that stellar explosions have repeatedly influenced biological evolution through environmental stress, genetic mutation, and ecosystem disruption. The cosmic ray bombardment associated with nearby supernovae increases mutation rates in living organisms. While most mutations are harmful or neutral, some provide beneficial adaptations that natural selection can act upon. The enhanced genetic variation created by cosmic ray exposure might have accelerated evolutionary processes during critical periods in Earth's history. Some researchers have proposed that the supernova events occurring 2 to 6 million years ago, recorded in iron-60 deposits, coincided with important evolutionary developments in human ancestors. The transition from Australopithecus to early Homo species occurred during this time frame, raising the intriguing possibility that cosmic radiation might have contributed to the genetic changes that ultimately led to human intelligence. This hypothesis remains highly speculative, but it illustrates the complex web of cause and effect linking stellar death to biological evolution. If cosmic events did influence human evolution, then our very existence as an intelligent species might depend on the same stellar explosions that now threaten our survival. The creative potential of supernova extends to their role in galactic ecology. These explosions inject enormous amounts of energy into the interstellar medium, creating cavities and bubbles that shape the structure of galaxies. Our solar system currently resides within the local bubble, a cavity roughly 300 light-years across that was carved out by multiple supernova explosions over the past 14 million years. This bubble provides a partially protective environment with lower than average cosmic ray intensities and reduced interstellar dust density. The formation of such bubbles may be crucial for the development of long-lived planetary systems, creating galactic safe zones where complex life can evolve without constant bombardment by cosmic radiation or disruption by stellar explosions. On even larger scales, supernovae drive galactic chemical evolution, gradually increasing the metallicity of galaxies over cosmic time. Early galaxies formed shortly after the Big Bang contained only primordial elements and could not support the formation of rocky planets or complex chemistry. Only after billions of years of stellar evolution and supernova explosions did galaxies accumulate sufficient heavy elements to support planet formation and potentially life. This process creates a cosmic timeline for the development of complexity. The first potentially habitable planets could not have formed until the universe was several billion years old, and supernova explosions had enriched the interstellar medium with sufficient heavy elements. Earth formed relatively late in this timeline, roughly 9 billion years after the Big Bang, when the galaxy had been sufficiently enriched by countless stellar deaths. The implications for astrobiology are profound. If supernovae are essential for creating the chemical preconditions for life, then potentially habitable worlds should be more common in regions of galaxies with active star formation and frequent supernovae. However, these same regions pose greater threats to existing life through cosmic ray bombardment and direct stellar explosions. This creates what astronomers call the Goldilocks zone for galactic habitability. Regions that have experienced enough supernova activity to be chemically enriched, but not so much as to sterilize developing biospheres. Our solar system may currently occupy such a zone, having benefited from past stellar deaths while remaining far enough from active star-forming regions to avoid frequent dangerous explosions. Looking toward the future, the creative aspects of supernovae will continue long after their destructive effects have faded. If a nearby supernova were to occur, the heavy elements dispersed by the explosion would eventually be incorporated into new generations of stars and planets. The catastrophe that devastated Earth's biosphere would simultaneously sow the seeds for future worlds, potentially more chemically complex and diverse than those that existed before. In this cosmic perspective, destruction and creation are not opposing forces, but complementary aspects of a single process. The universe creates complexity through catastrophe, builds chemical diversity through stellar death, and enables life through cosmic violence. Every breath we take contains oxygen forged in the heart of an exploding star. Every heartbeat depends on iron scattered by cosmic explosions. This realization should inspire both humility and wonder. We are not separate from the cosmic processes that govern the universe. We are products of those processes, temporary arrangements of stellar ash animated by the same nuclear forces that power the stars. Our existence is both improbable and inevitable. Improbable because it depends on an intricate chain of cosmic events stretching back billions of years. Inevitable because the laws of physics ensure that given enough time and space, stellar death will create the conditions for stellar birth, and with it, the possibility of worlds complex enough to contemplate their own origins. The next supernova in our vicinity will indeed bring destruction, but it will also continue the grand cosmic cycle of death and rebirth that has been operating since the first stars illuminated the primordial darkness. In destroying one world, it may create the conditions for countless others, scattering the elements of Earth's biosphere across interstellar space where they might someday be incorporated into alien worlds under foreign suns. Perhaps this is the ultimate perspective we need when contemplating cosmic catastrophe, not as a meaningless random event, but as part of the ongoing creative process that has shaped the universe since its beginning. We are witnesses to and participants in the greatest story ever told, the saga of how the cosmos creates complexity from simplicity, life from lifelessness, and consciousness from cosmic dust. In facing the threat of nearby supernovae, we confront both our mortality and our immortality. Our individual lives and civilizations are fragile, temporary arrangements that cosmic forces can erase in an instant. But we are also permanent participants in the cosmic process of creation, our atoms destined to survive any catastrophe and eventually find their way into new forms, new worlds, new possibilities for complexity and consciousness. The stars that threaten us also define us. In understanding this paradox, we find not despair, but a deeper appreciation for our place in the cosmic story. Bit players in an epic tale of destruction and creation that spans the universe and stretches across eternity. Faced with the ultimate cosmic threat, humanity would be forced to undergo the most rapid and fundamental transformation in our species' history. The response to a nearby supernova would not simply be a matter of engineering better shelters or developing new technologies. It would require a complete reimagining of what it means to be human in a hostile universe. The immediate response would likely follow patterns established for other large-scale disasters, but the unprecedented nature and duration of the supernova threat would quickly overwhelm existing emergency management frameworks. Civil defense organizations are designed to handle temporary crises, earthquakes that last minutes, hurricanes that persist for days, even pandemics that might continue for years. A supernova's effects would endure for millennia, requiring not emergency response but permanent adaptation. Government responses would vary dramatically based on existing institutional capacity, technological resources, and social cohesion. Nations with advanced space programs, robust scientific institutions, and experience managing complex technological systems would have significant advantages. Countries like the United States, members of the European Union, Japan, and China possess the technical expertise and manufacturing capacity necessary to develop protective technologies rapidly. The first priority would be protecting critical infrastructure and essential personnel. Nuclear power plants would require enhanced radiation shielding and backup systems to prevent meltdowns in the enhanced cosmic ray environment. Hospital facilities would need protection for both patients and medical equipment. Government command centers would be hardened against radiation and equipped with independent life support systems. Military installations would become crucial refuges for both their inherent protective capabilities and their existing stocks of specialized equipment. Underground command bunkers designed to survive nuclear attacks would provide some of the safest environments on Earth during the cosmic ray bombardment. Military logistics systems would be essential for distributing food, medical supplies, and equipment to civilian populations. The space industry would face unique challenges and opportunities. Existing satellite constellations would be degraded or destroyed by enhanced cosmic radiation, creating immediate needs for replacement systems with improved radiation hardening. Paradoxically, space-based manufacturing might become more important than ever, as orbital facilities could potentially produce materials and components impossible to manufacture on Earth's surface under enhanced radiation conditions. International cooperation would become both more necessary and more difficult than ever before. The global nature of the supernova threat would require unprecedented coordination of resources, information, and technology. However, the breakdown of normal communication systems and the internal focus required for national survival might impede the multilateral cooperation most needed during the crisis. The scientific community would experience a fundamental shift in priorities and methodologies. Basic research would be subordinated to immediate survival needs, with massive resources redirected toward radiation protection, agricultural adaptation, and closed-loop life support systems. Field research would become extremely difficult or impossible in many disciplines, forcing scientists to adapt to laboratory-based and computational approaches. Universities would need to balance their traditional roles as centers of learning and research with their new importance as potential refuges for populations seeking protection. Campus infrastructure, often including the underground tunnel systems, large buildings suitable for conversion to protected spaces, and existing technical expertise, would make academic institutions valuable community resources. The development of protective technologies would proceed along multiple parallel tracks. Radiation-resistant electronics would be essential for maintaining communication systems, monitoring equipment, and automated systems. Advanced materials research would focus on UV-blocking films, radiation-absorbing composites, and self-repairing systems capable of functioning in high-radiation environments. Agricultural technology would require complete reinvention. Traditional outdoor farming would be impossible, necessitating rapid deployment of protected growing systems. Hydroponics, aeroponics, and other soil-less cultivation methods would become critical technologies. Genetic engineering of crops for enhanced radiation resistance would be accelerated, though the time required for developing and testing new varieties would create dangerous delays. Urban planning would shift toward underground and enclosed spaces. Cities would need to construct extensive tunnel networks connecting residential areas to essential services. Existing subway systems would be expanded and repurposed as transportation arteries for a largely subterranean civilization. Architecture would emphasize radiation shielding, air filtration, and psychological comfort in enclosed spaces. The energy sector would face conflicting demands for expanded generation capacity and reduced surface exposure for maintenance personnel. Nuclear power might become more attractive despite its risks, as it provides large amounts of energy without requiring surface installations vulnerable to cosmic radiation. Geothermal energy would gain importance as a source unaffected by atmospheric conditions. Manufacturing industries would need to adapt to producing goods under protective conditions. Factories would require enclosed, radiation-shielded environments with sophisticated air filtration systems. Supply chains would be disrupted by transportation difficulties and the need to protect workers throughout the production process. The medical system would expand dramatically to address both acute radiation effects and long-term health monitoring. New specialties would emerge focused on cosmic radiation medicine, while existing fields like dermatology and oncology would see massive increases in demand. Pharmaceutical production would need to increase rapidly to supply treatments for radiation sickness and cancer. Social and psychological support systems would become crucial for maintaining mental health in a confined, high-stress environment. Traditional outdoor recreational activities would be impossible, requiring the development of new forms of entertainment and exercise suitable for enclosed spaces. Virtual reality and other immersive technologies might become essential tools for psychological well-being. Education systems would face the challenge of preparing children for life in a permanently altered world while maintaining cultural continuity. Curricula would need to emphasize practical skills for survival in protected environments while preserving knowledge and values from the surface-dwelling civilization. Physical education would require complete redesign for enclosed spaces. Religious and philosophical institutions would grapple with the theological and existential implications of cosmic catastrophe. Some might interpret the supernova as divine judgment, while others would struggle to maintain faith in a benevolent universe. New spiritual movements might emerge focused on humanity's relationship with cosmic forces and our place in an apparently hostile cosmos. Economic systems would require fundamental restructuring. Market mechanisms designed for growth and expansion would need adaptation to resource-constrained survival conditions. Currency systems might shift toward resource-based measures of value, with energy, food, and protective materials becoming the new basis of wealth. The entertainment industry would need to adapt to serving populations confined to protected spaces while maintaining morale during an extended crisis. Digital entertainment would become more important, while live performances would require new formats suitable for enclosed venues. Sports would need modification for indoor environments, while new competitions might emerge based on skills relevant to survival. Legal systems would confront novel questions about resource allocation, population movement, and individual rights during extended emergency conditions. Traditional concepts of property rights would be challenged by the need for collective survival measures. International law would struggle to address global migration flows and resource-sharing arrangements. Innovation would be driven by desperate necessity rather than market forces or academic curiosity. The most crucial advances would likely occur in radiation protection, closed-loop life support, food production, and psychological adaptation to confined environments. Patent systems and intellectual property protections might be modified or suspended to accelerate the sharing of survival-critical technologies. Long-term adaptation would require humanity to develop into a fundamentally different kind of species. Future generations would grow up in enclosed environments, potentially developing different physical characteristics and psychological profiles than surface-dwelling humans. Social structures would evolve to support permanent underground communities with limited resources and confined spaces. The most successful human communities would likely be those that could maintain technological capability while developing sustainable closed-loop systems for all essential resources. Self-sufficiency in food production, energy generation, waste recycling, and manufacturing would become the hallmarks of viable civilization. Cultural evolution would accelerate as communities adapted to radically different living conditions. New art forms might emerge suited to enclosed spaces and artificial lighting. Music could evolve to work within the acoustic constraints of underground environments. Literature might develop new themes focused on survival, cosmic perspective, and the relationship between humanity and the universe. Perhaps most significantly, the supernova crisis would force humanity to confront its assumptions about progress, growth, and our relationship with the natural environment. The modern lifestyle of expansion, consumption, and environmental exploitation would be revealed as unsustainable in a hostile cosmic environment. Survival would require developing a steady-state civilization focused on stability, efficiency, and long-term sustainability. The generation that lived through the supernova event would become the founders of a new phase of human civilization, one defined by cosmic awareness, technological dependence, and adaptation to environmental constraints. Their children would inherit a world where cosmic threats are accepted facts of existence, where technology is essential for survival, and where humanity's relationship with the universe is fundamentally different from anything in our previous history. This transformation would not necessarily represent decline or failure. Instead, it might mark humanity's evolution into a mature cosmic civilization, one capable of surviving in a universe where stellar death is a regular occurrence, where cosmic radiation is a constant threat, and where long-term survival requires accepting our place in a vast, dynamic, and often dangerous cosmos. The skills, technologies, and social systems developed in response to a supernova threat would also prepare humanity for other cosmic challenges. Asteroid impacts, solar flares, gamma-ray bursts, and the eventual need to establish self-sufficient colonies beyond Earth. In adapting to survive stellar death, we might inadvertently prepare ourselves for becoming a truly interstellar species. Somewhere in the Milky Way, at this very moment, a massive star is dying. Its nuclear fires are guttering out after millions of years of steady burning. Its core is contracting, growing denser and hotter with each passing day. The delicate balance between gravity and radiation pressure that has sustained the star throughout its lifetime is beginning to fail, and physics has already written the inevitable conclusion to this cosmic story. When that star finally collapses, whether tomorrow or in 100,000 years, it will unleash forces that dwarf human comprehension. In less than a second, it will release more energy than our sun will produce over its entire 10 billion year lifetime. The explosion will create temperatures exceeding those that existed in the first moments after the Big Bang. It will forge elements that cannot be made anywhere else in the universe and scatter them across thousands of light years of space. If this stellar death occurs within our cosmic neighborhood, it will forever change the trajectory of life on Earth. The familiar blue skies of our childhood will be replaced by alien hues that speak of a damaged atmosphere. The gentle sunlight that has nurtured life for billions of years will become a source of danger, forcing humanity into underground refuges. The open landscapes that have shaped our evolution and culture will become as hostile to human life as the surface of Mars. Yet even in contemplating this cosmic catastrophe, we must remember that it would also represent the continuation of the very process that made our existence possible. The iron in our blood was forged in the heart of an exploding star. The calcium in our bones was scattered across space by stellar death. The gold in our technology, the uranium in our power plants, the rare earth elements in our electronics, all are the ashes of ancient supernovae that exploded billions of years ago. We are not victims of cosmic violence, we are products of it. Every atom in our bodies except hydrogen has been processed through the nuclear furnaces of dying stars. We are, quite literally, made of stardust, the debris of stellar explosions that occurred long before our solar system existed. This cosmic inheritance shapes more than just our physical composition, the chemical complexity that makes life possible, the heavy elements that allow rocky planets to form, the energy gradients that drive biological processes, all depend on the ongoing cycle of stellar death and birth that has operated throughout cosmic history. The recent discoveries that have motivated this exploration, the iron-60 in ocean sediments, the beryllium-10 spikes in seafloor crusts, the evidence for multiple supernova events affecting Earth over the past 10 million years remind us that this is not an abstract threat from the distant future. Our planet has already been shaped by nearby stellar explosions and will be again. The challenge facing humanity is not whether we will encounter cosmic catastrophe, but whether we will be prepared when it arrives. The universe operates on timescales that dwarf human history. Our entire recorded civilization spans less than 10,000 years, while the supernova cycle operates over millions of years. From a cosmic perspective, we are newcomers to a galaxy where stellar death has been occurring for over 13 billion years. But perhaps this cosmic perspective offers hope as well as humility. If life on Earth has survived multiple supernova events over the past few million years, if ecosystems have recovered from cosmic ray bombardment and ozone depletion, if evolution has continued despite periodic stellar catastrophes, then life itself may be more resilient than we imagine. The key insight is that survival and adaptation are possible, but they require accepting our place in a dynamic, dangerous universe. The romantic notion of Earth as a safe haven isolated from cosmic violence is simply wrong. We live on a planet orbiting a star in a galaxy where stellar explosions regularly occur, where cosmic radiation varies over time, and where our continued existence depends on maintaining the delicate balance of conditions that makes our world habitable. Understanding this reality should motivate rather than discourage us. If cosmic threats are inevitable on geological timescales, then developing the capability to survive them becomes one of humanity's most important long-term goals. The technologies, social systems, and knowledge base required to survive a nearby supernova would also prepare us for other cosmic challenges and enable our expansion beyond Earth. The supernova threat highlights the importance of several crucial areas for human development. Space technology becomes not just a tool for exploration, but an essential component of species survival. The ability to monitor cosmic threats, establish self-sufficient settlements beyond Earth, and maintain technological civilization under adverse conditions may ultimately determine whether humanity remains a single-planet species vulnerable to cosmic catastrophe or becomes a robust interplanetary civilization capable of surviving stellar death. Scientific research takes on new urgency when viewed through the lens of cosmic threats. Understanding stellar evolution, atmospheric chemistry, radiation biology, and closed-loop life support systems becomes more than academic curiosity. It becomes survival preparation. The fundamental research being conducted today in universities and laboratories around the world may someday provide the knowledge needed to preserve human civilization against cosmic catastrophe. International cooperation becomes essential when facing threats that affect the entire planet equally. Supernovae do not respect national boundaries, political ideologies, or economic systems. The response to such threats requires the combined resources, knowledge, and capabilities of all human societies working together toward common survival goals. Perhaps most importantly, the supernova threat forces us to confront our assumptions about progress, growth, and our relationship with the environment. The modern industrial civilization that has transformed Earth's surface over the past few centuries is fundamentally dependent on stable cosmic conditions that we often take for granted. Learning to thrive in a dynamic cosmic environment may require developing more sustainable, resilient, and adaptable forms of civilization. The children growing up today will inherit both the benefits and the challenges of living in a cosmic age. They will have access to knowledge about the universe that previous generations could never have imagined, from the detailed structure of distant galaxies to the precise mechanisms of stellar death. But they will also live with the awareness that Earth exists in a universe where catastrophe is always possible, where cosmic forces operate beyond human control, and where long-term survival requires constant vigilance and adaptation. This cosmic awareness should inspire rather than intimidate. Throughout human history, our greatest achievements have come from confronting and overcoming seemingly impossible challenges. We have survived ice ages, developed agriculture, built civilizations, explored the oceans, learned to fly, traveled to the moon, and begun to understand the fundamental laws governing the universe. The Supernova Challenge represents the ultimate test of human ingenuity, cooperation, and resilience. Meeting this challenge would require developing technologies that exceed our current capabilities, social systems that transcend our current divisions, and knowledge that expands our current understanding. But success would transform humanity into a species capable of thriving anywhere in the universe, under any cosmic conditions. Standing beneath the night sky, aware of both the beauty and the danger represented by those distant points of light, we face a choice that will define humanity's future. We can continue to live as though Earth exists in cosmic isolation, vulnerable to the stellar explosions that will inevitably occur in our galactic neighborhood. Or we can begin the long process of becoming a mature cosmic civilization, one that understands its place in the universe, prepares for cosmic threats, and develops the capability to survive and thrive among the stars. The next supernova in our vicinity may bring destruction to the world we know, but it will also test whether humanity has earned its place as a permanent member of the cosmic community. The atoms forged in stellar death have already given us life. Whether we use that gift wisely enough to survive the next stellar explosion will determine our species' ultimate destiny among the stars. In the end, we return to where we began, contemplating the death of distant stars and wondering what it means for life on Earth. But now we understand that this is not just an abstract scientific question or a source of apocalyptic anxiety. It is the fundamental challenge that will define humanity's future, the test that will determine whether we remain children of Earth or become citizens of the cosmos. The stars that made us will also test us. How we respond to that test will determine not just our survival, but our transformation into something greater than we have ever been. In facing the death of stars, we confront the possibility of our own transcendence, from a planetary species to a cosmic one, from temporary arrangements of stellar ash to permanent participants in the ongoing story of the universe. The supernova is coming. The only question is whether we will be ready.